Hello everyone. This video is a continuation of the previous two parts which we did on chemical energetics. In this one, we're going to talk about the enthalpy change of solution, hydration, and we're going to talk about the factors which affect hydration. We're going to see the solubility of group 2 hydroxides and sulfates. We're going to also talk a little bit about ion polarization. To begin with, let's look at this as a cycle. We have the ions which are in their gaseous states, and we are converting them into the solid ionic compound. And we know converting them from a gaseous ion to solid ionic compound is called enthalpy change of lattice energy. Okay, now we can see we have implemented two more enthalpy changes in this Hess cycle. Firstly, let's talk about the hydration one. So one on the left. We can see we're going from the gaseous ion into the ion which is in its aqueous state. So this is known as enthalpy change of hydration when we go from the gaseous ion into an ion which is in its aqueous state. And for enthalpy change of solution, we are doing the same thing. We are going into the ion which is in its aqueous state. However, we are going from the solid ionic compound. Now, using this as a cycle, we can form this equation, which is enthalpy change of solution equals to enthalpy change of hydration minus enthalpy change of lattice energy. Okay, before we move, let's look at the definition for enthalpy change of hydration. The enthalpy change of hydration is when 1 mole of a specified gaseous ion dissolves in sufficient water to form a dilute solution. Okay, now we can talk about the factors which affect hydration. So if our ionic charge increases, that means that the attraction between the ion and the dipole increases. This means that the enthalpy change of hydration also increases. Secondly, if our ionic radius decreases, it would mean that our charge density has increased because we know charge density is equals to the charge divided by the size. So our enthalpy change of hydration also increases. With this, we can understand that down the group, the enthalpy change of hydration will become less exothermic. This is because down a group, the ionic radius increases, which means the charge density decreases. So now you can look at this simplified version. We have the gaseous ion, and we are reacting it with the water molecule. So the water molecule has an oxygen atom, which is very electronegative. So it pulls all of the electrons to itself and gains a partially negative charge. This partially negative charge is attracted to the magnesium gaseous ion, which is positively charged. And this reacts to form the magnesium ion, which is now in aqueous state. Okay, now let's look at the enthalpy change of solution. The enthalpy change when 1 mole of an ionic solid is dissolved in sufficient water to form a very dilute solution. So basically we can see we have the ionic solid and we dissolve it into AQ, which means sufficient water to form the ions which are in their aqueous states. Alright, now let's look at this quirk. If our enthalpy change of solution has a large positive or a small negative value, it means that the compound is insoluble. And on the other hand, if it has a large negative value or a small positive value, that means that the compound is soluble. Alright, now we can look at the trends of group 2 hydroxides and sulfates. We're going to talk about their solubility. Before we begin, let's look at this equation which we saw in the first part of the video. We can see we have the enthalpy change of solution, which is equals to enthalpy change of hydration minus the enthalpy change of lattice energy. You have to understand that hydration and lattice energy are both exothermic, so they both have a negative value. Okay, before we move, you have to understand that hydroxides solubility increases down the group and sulfate solubility decreases down the group. We know this from AS. Now our main part is to explain why this is the case. Answer for solubility, you have to look at the enthalpy change of solution value. If it is more exothermic, it means that the compound is more soluble. If the enthalpy change of solution is less exothermic, it means that the compound is less soluble. Okay, now let's look back in this equation. This value of hydration is exothermic. That means it has a negative value. And same with this value, this lattice energy has an exothermic value. That means it has a negative value. However, it means that this negative value and this negative sign is going to make it a positive value. So let's look at this. This enthalpy change has this negative part and this positive part. Now, if we want this enthalpy change to be more exothermic, that means we have to increase this or we have to decrease this. Because if this value decreases, that means the entire value is going to be more negative. Okay, Now we have to understand that as we go down a group, both enthalpy change of hydration and lattice energy is going to decrease. That means both of these values will decrease. However, if this value decreases less than this value, that means the entire answer is going to be more negative. That means it's going to be more exothermic. That means the solubility is going to be more. That is exactly what we have written over here. Hydroxide solubility increases down the group. Down the group, both hydration and lattice energy decreases. So both of these values is going to decrease. However, the lattice energy will decrease more compared to this value of hydration. So if this value of lattice energy decreases more, if this positive value decreases more than this negative value, that means the entire answer is going to be more negative. That means the enthalpy change of solution is going to become more exothermic. And that means the solubility is going to be more. And we're doing the same thing for sulfates as well. The solubility of sulfates is going to decrease down the group. And as we go down the group, the enthalpy change of hydration and lattice energy both decrease. However, the enthalpy change of hydration is going to decrease more compared to the enthalpy change of lattice energy. So if you look back over here, this enthalpy change of lattice energy is going to decrease less. And this enthalpy change of hydration is going to decrease more. So the entire answer is going to be less exothermic. That means it is going to be less soluble. So enthalpy change of solution becomes less exothermic and the solubility decreases down the group. Okay, so before we move on, let's look at this question to understand how to use our equation or how to form the Hesse cycle. So we are given with the values of solution, lattice energy, and hydration. We are asked to find the enthalpy change of hydration of this potassium gaseous ion. So to begin with, we have to first construct the Hesse cycle. As you can see, I have did that over here. First, we start with the elements which are in their ion forms in gaseous states, and we convert them into the solid ionic compound. And this conversion from this gaseous ions to 1 mole of solid ionic compound is called enthalpy change of lattice energy. And what we learned today was that the enthalpy change of hydration is basically when we take these gaseous ions and convert them into aqueous ions. And for enthalpy change of solution, we saw when we take this potassium solid ionic compound and we convert it into its aqueous ions is known as enthalpy change of solution. So using Hesse cycle, we write this equation, which you can also memorize. Enthalpy change of solution is equal to enthalpy change of hydration minus lattice energy. And then we just put the values. So enthalpy change of solution, we have a value of 21 over here. And for hydration, which is going from here till here, we can see that we are given with one of the values, which is for iodine. However, we are asked to find the value for potassium. So we just write that over here, and then we give a negative sign for this. And then we have the value for lattice energy, which is itself negative. And then we just solve this equation to find the value for potassium ion. Okay, now let's talk about ion polarization. Basically, we have the magnesium ion, which is positively charged. It is attracting the carbonate ion. It is attracting the electrons in it. We can see it has 4 atoms. That means it has a lot of electrons. And this spherical shape, as you can see over here, is being distorted. This is called ion polarization. The carbon-oxygen bonds become weaker. So the thermal stability for both fructocarbonates and nitrates increases down the group. This is because of charge density of the elements. We know that the charge density of the elements will decrease down the group. This is because they have a constant charge down the group, plus 2. However, their size increases as their atomic radius increases, which means that the charge density of the elements becomes lower. That means that the power of distortion becomes lower. That means that the stability increases.